Hello and welcome to the next lesson. In this lesson we'll be looking at magnetism and electromagnetism, as well as some of the characteristics and properties around magnets. So let's get started. Over the course of this presentation, we will look at the different properties of permanent magnets. We will also look at compasses and the application of some magnets. We will then look into electromagnets. We will then try to determine the polarity of an electromagnet when we know the direction of the current. Throughout the presentation, we'll look at a various number of definitions used to describe magnetism and magnetic quantities. Magnets can occur naturally in nature. And some of the earliest magnets known are found in the Asia Minor region, which we now know as Turkey. This region is also known as Magnesia. And from that location, we get the name magnetite, which then derives into our current term of magnet. It was noted or noticed that magnetite attracted iron. As time progressed, somewhere along the way, someone realized that if a magnet was allowed to rotate somehow, that it would always point in the same direction. This led to the invention of a compass. Pictured here are a couple examples of some very early compasses. Some of the earliest versions of compasses have actually been found in China. A compass is just a piece of magnetic material. And if it's allowed to rotate, the magnetic field of the rock, stone, or metal will line up with the Earth's magnetic fields. And it'll always point towards the North Pole of the planet. The North Pole of the compass will point towards the North Pole of planet Earth. But here's the interesting part. When it comes to magnets, opposites attract. The North Pole of the compass is actually attracted to the magnetic South Pole of the planet Earth. So bearing that in mind, the magnetic South Pole of Earth is actually located in the northern hemisphere near the North Pole of the planet. And the magnetic North Pole of Earth is actually close to the South Pole of planet Earth. Magnets come in a variety of different sizes and shapes and configurations. Permanent magnets require energy to be created, but they don't require any energy to maintain their field once they're created. This is one of the basic laws of magnetism. Man-made permanent magnets are much stronger than anything that occurs naturally. Some of the best magnets that we make now are made out of ceramics. We think that materials get their magnetic properties from electrons spinning on their axes, much the same as planet Earth spins on its axis to give us day and night. The spinning action of the electron on its axis gives the electron a little magnetic moment or domain. In a non-magnetized material, these domains tend to cancel each other out, so that the overall magnetic property of the material is zero. A magnetic material has a number of these domains lining up, so that the little magnets of the electrons spinning on their axes will add together to form a much larger magnetic force. Ferromagnetic materials, such as iron, nickel, and cobalt, have these magnetic domains associated with their electrons. When these domains are in a disarray, or randomly spread around, the material is not magnetized. But if we can get these domains to line up, then the material will become magnetized. So if all these little domains, represented here by a bunch of little bar magnets with north and south poles, can all be lined up the same way, if we can put pressure on them somehow, then the material will become magnetized, where all the little magnets will come together to form a larger magnetic field. And if we take even more of these pieces and put them together, such as taking little magnets and putting them together, we end up with a much larger and stronger magnet. Or, if we take a big magnet and break it into pieces, then we end up with a bunch of smaller magnets. Let's look at the magnetic domains another way. We can represent the magnetic domain, or magnetic moment, by a sphere with an arrow indicating its magnetic polarity. Here in this red sphere, the magnetic north is pointing up. Here, an opposite magnetic pole is pointing down. It's theorized that these two electrons are spinning in opposite directions, giving them different magnetic moments or polarities. In a non-magnetized material, these magnetic moments would spin randomly in different directions. And for the most part, the overall magnetism would cancel each other out, leaving us with a net zero magnetic field. If we can find a way to get those magnetic moments to point in the same direction, then all of those little tiny magnets associated with the spinning axes of the electrons will give us a larger magnetic force. If we can get enough magnetic moments and enough molecules to point the same way, then our material will become magnetized. You will notice in this particular material that most, but not all, of the domains are pointing the same way. If we can get all the domains in a piece of material all pointing the same way, then the material is what we call saturated. And that's when all the possible magnetic domains are all lined up the same way. Where if we add more magnetizing force, it will not result in more magnetic output. That's because our material is at its maximum magnetic potential. Maximum magnetic potential is what we call magnetically saturated, or the point of saturation. Magnetic materials set up lines of force. These magnetic lines of force we call flux. We use the Greek letter symbol phi to represent flux. Magnetic lines of force, or flux lines, always repel each other. They have a north to south direction, and they never cross. Magnetic flux lines form north and south poles. And like most things in nature, dissimilar or unlike poles will attract. But like poles or similar poles will repel each other. If we take a permanent magnet, put it underneath a piece of paper, and sprinkle iron filings over it, we can actually visually see these magnetic lines of force. These magnetic lines of force, or flux lines, don't flow, but they do have a north to south direction. Here I have a bar magnet, and I have some iron filings. I recorded this in my classroom. I take a piece of paper and I put over top of it. Now I'm going to gently sprinkle some iron filings over top of the magnet. You can see the iron filings lining up with the magnetic lines of force, or the flux lines. And you can clearly see how they are laid out as they travel from north to south. They are not moving. Flux lines do not move. They also do not cross. The more flux lines I have per unit area, the higher the flux density. The higher the flux density, the stronger the magnetic field. We need a few definitions before we can carry on. The first one is reluctance. You can think of reluctance as sort of being resistance to magnetic circuits, where reluctance is the opposition to setting up magnetic lines of force, or flux. We've already talked about saturation. Saturation occurs when all the magnetic domains of a material are lined up, where adding more magnetizing force will not result in any more magnetic activity. The material is at its magnetic potential. Residual magnetism is the amount of magnetism that is left behind after a magnetizing force has been removed or stopped. Retentivity is a material's ability to retain magnetism after a magnetizing force has been removed. Retentivity is when a material retains some of the residual magnetism. Finally, there's permeability. Permeability is when a material is able to or permits the setting up of magnetic lines of flux. A high permeable material easily sets up lines of flux and will conduct them. Magnetic lines of flux will actually go out of their way to go through a highly permeable material, such as soft iron. There are three classifications of magnetic materials. These are materials that have magnetic properties. Now, these are by no means a complete definition or classification of these materials. They are just a very simplified and basic classification. We're a ferromagnetic material, which is a ferrous material, such as iron or nickel. These materials easily set up magnetic lines of flux, and they tend to have a high retentivity. So they tend to retain the magnetism after the magnetizing force has been removed. Paramagnetic materials are not easily magnetized, and they tend to have a low retentivity. They don't tend to hold on to their magnetism for a very long time. It also takes a great deal of effort to magnetize them. Diamagnetic materials are the most important to us in the electrical sense. Diamagnetic materials tend to have no retentivity. They can be magnetized, but they lose their magnetism as soon as the magnetizing force has been removed. We can see this in motors, transformers, solenoids, where when we turn on the current and magnetize them, they have a magnetic field. But the moment we remove the magnetizing force, current, the field collapses and turns off almost instantaneously. It's the properties of diamagnetic materials that allow us to have motors, transformers, and solenoids, and other such magnetic machines. Here we can see an example of a bar magnet, which is labeled north and south. And the magnetic lines of force are drawn in for us. Air is considered to have a high reluctant path. If we were to put a piece of soft iron near the magnet, soft iron has a low reluctance or a high permeability. The magnetic lines of force will actually stretch and go out of their way to go through the low reluctant path or the path with a high permeability. Permeability is just the opposite of reluctance. It permits the lines of force to flow easily. This allows us to provide magnetic shielding. A high permeable core or material also allows us to concentrate the lines of flux. When we have more lines of flux in a given area, we say that it has a high flux density. The more flux we have per unit area, the more lines of force we have that are concentrated, the stronger the magnetic field will be in that area. We think that magnetism comes from the little magnetic domains, or moments, associated with electrons spinning on their axes. So effectively, magnetism is directly tied to electrons. If we can find a way to get those electrons all to line up one way, then we can easily magnetize a material. Here, we have a very simple electromagnet, where we have a piece of wire wrapped around a nail. And we take that piece of wire and we attach it to a battery. And as the current flows through the wire, well, all the electrons are flowing from the negative to the positive. For all my examples, I will be referring to electron flow, where the actual flow of the electrons is from the negative terminal of the source to the positive terminal of the source. So keep that in mind. All of my references will be with electron flow in mind. As the current passes through the wire, all the electrons are forced to line up in the same direction because they're all flowing in the same direction. Since all the electrons are going the same way, then all of their domains, their magnetic domains, line up in the same direction as well. Lining up all the domains in the copper then increases my overall magnetism. My nail acts as a soft iron core or a high permeable material, which concentrates my flux. It makes my electromagnet more effective. And so that when I turn it on, I have a magnetic field. And I'm able to pick up small objects with my simple battery nail electromagnet. And I can pick up such things as paper clips. So let's look at our electromagnet in a little bit more detail. Whenever current passes through a wire or a conductor, a magnetic field is set up around the conductor. This is because of the flow of the current. The current flows through the conductor. Current is the flow of electrons. Our magnetic moments, or domains, are associated with my electrons. So by forcing all my electrons to move in the same direction, I force my magnetic domains to also line up in the same direction. That causes a magnetic field to form around the perimeter of the wire. It actually forms like a cylinder or a tube around the wire. In the case of electron flow, where the electrons are flowing from negative to positive, we can determine the orientation of the magnetic field around the wire by grabbing the wire with our left hand and pointing our thumb in the direction of the current. So if you imagine yourself grabbing this wire with your left hand, with your thumb pointing in the direction of the indicated red current, I, you will see that your fingers would wrap around the wire in the same direction as the blue indicated magnetic field. We can determine the direction of the magnetic field, or the polarity of the magnetic field, around a current-carrying conductor by using the left-hand rule for conductors. Since we are doing electron flow, where the flow of current goes from the negative terminal to the positive, we use the left hand. If you are doing conventional current flow, whereas the idea is that current flows from positive to negative, you need to use your right hand. But I will be using electron flow. So my example will use the left hand. You can sort of think about the conductor, the current carrying conductor, like an arrow, where you would grab the arrow in a fashion that your thumb would point in the direction that the arrow would fly. Now, it's not the arrow that we're concerned about. It's the direction of the current. So your thumb would point in the direction of current. The way your fingers wrap around the conductor is the way the lines of force or the magnetic field would set up around the conductor. We use a convention to indicate on a piece of paper or a flat surface which way the current is traveling. If we were to look at the tip of the arrow, we would see the point of the arrow coming at us. So we use a circle with a dot to indicate that the current is moving towards you or out of the page, so that it looks like we are looking at the tip of the arrow. If we take our left hand and point our thumb in the direction of the tip or out towards you, then our fingers would wrap around the conductor in the direction of the magnetic field, which in this case is clockwise. If we were to look at the back end of the arrow, it would look like the tail feathers of the arrow are going away from us. So we use a cross or a plus sign to symbolize that the current is going away from us, just like the tail feathers of the arrow. So that if you use your left thumb and point your thumb towards the board or your piece of paper, your fingers would then indicate that the magnetic field is setting up in a counterclockwise direction around the conductor. We can use the left-hand rule to determine how the magnetic field is setting up around a conductor on a flat surface. The direction of the magnetic field around a wire is dependent upon the direction of the current. The red arrow indicates the direction of the current through the current carrying conductor. If you were to take your left hand, because we're using electron flow, and grab the wire with your left hand and point your thumb in the direction of the current, which in this diagram is from left to right, the direction your fingers are wrapped around the wire would indicate the direction of the magnetic field, which is counterclockwise in this diagram. If we were to change the direction of the current, now from right to left, and you were to grab the conductor with your left hand, again pointing your thumb in the direction of the current, you would notice that the direction of the magnetic field also changed. So in this second diagram, the magnetic field is in a clockwise direction. So, again, as a convention or a representation on paper, a circle with a dot into it in the middle indicates that the current is coming out or flowing out of the flat surface towards you. So that if you take your left hand and point your thumb out of the paper towards you, your fingers would indicate that the magnetic field is rotating in a clockwise direction. A circle with a cross in it, or a plus sign, would indicate that the current is flowing away from you, or into the paper. Taking your left hand and pointing your thumb towards the surface, your fingers would then indicate that the magnetic lines of flux would set up in a counterclockwise direction. Using this convention, we can determine how a magnetic field is setting up around a current-carrying conductor. This magnetic field sets up along the entire length of the conductor. If we take a current-carrying conductor, here the current is going away from you or into the board. And we take a second current-carrying conductor, doing the same. And we bring those two current-carrying conductors together. The magnetic fields from those two current-carrying conductors will then combine to produce a much larger field around the system. This is what happens when we coil a wire around a central core. The magnetic flux from each current-carrying conductor combines with the wire next to it to increase the overall magnetism of the system. As we continue to add more coils, or more loops, or more turns, together with the current going in the same direction, our overall magnetism increases. So now we have what we call an inductor, or a coil, where we've taken our wire and we've formed a coil with it. Magnetism is produced in the coil by current traveling through the conductor. The current forces the magnetic domains of the copper to go in one direction. When we have all of those domains lined up in the same direction, then we have some magnetism. Increasing the number of loops or turns in a coil increases the magnetism, because the magnetism of one wire sitting next to another one will add its magnetic flux to the wire beside it. And as we continue to add more wires side by side, we will increase the overall magnetic flux. Thus, the magnetic field strength is directly proportional to its ampere turns. As we increase current until the point of saturation, we'll get more magnetism. If we increase the number of turns, we will get more magnetism. Thus, the magnetic field is proportional to the ampere turns. This is an important ratio when you go on to learn about transformers and transformer ratios. So far, we've discussed that as we add more current, we get more flux, or more magnetism. We've also stated that as we add more turns to a coil, we will also increase the amount of flux or magnetism for a given system. The third thing that greatly impacts our electromagnet, is a core material that is highly permeable. If you remember our definition, permeability is the ability of a material to set up lines of flux. Often, the core material is what the coil is actually wrapped around. If a coil does not have a highly permeable core, we refer to those as air cores. That's because they may not have any magnetic material in the center, and any non-magnetic material is considered the same as air. Often, cores are made from magnetic materials. These magnetic materials will concentrate the flux, which greatly increases the magnetic field strength. An iron core provides an easy path for lines of flux to set up. And so what it does is it takes all of the flux and concentrates it in one place, so that we have a high flux density. A higher flux density means that we have a stronger magnetic field. Core materials do not create flux. All that core materials do is they concentrate the flux that we already have. It gives them an easy path for them to flow, and so they concentrate themselves closer together. A high flux density means that I have a strong magnetic force. Core materials drastically improve the efficiency of our magnetic system. So what are the three main factors that improve or affect electromagnets? The first is by adding more turns or loops. More turns and more loops give me more domains to work together, or more magnetic fields that are around my wires. More magnetic fields because of more wires is going to give me a larger magnetic field. If I can improve the core material by giving it a highly permeable path that likes to set up lines of force or magnetic lines of flux, then I can concentrate those lines of flux, making them much more effective. Finally, current passing through the conductor is actually what creates my magnetic field. So, as I increase current, I increase the magnetic field. I cannot increase the current indefinitely. I can only increase the current until I get to the point of saturation. Saturation is the point at which all the magnetic potential for that system has been achieved. Where adding more current or more magnetizing force will not result in more magnetism. The overall effectiveness or strength of an electromagnet is directly related to the construction of the coil or electromagnet. If I increase the number of turns, I increase the overall magnetic potential. If I improve the core, the permeability of the core concentrates my flux, so it makes my flux much more effective. or more efficient. And again, the third thing that affects my magnetism, or my electromagnet, is my current. As I apply more current, I line up more magnetic domains. Lining up more domains means that I've created more flux. I can keep applying current until I reach the point of saturation. And again, saturation is a point where adding more current or magnetizing force does not increase the magnetic potential, because my system has already reached its maximum. We can also use the left hand to determine where the magnetic north pole is on an electromagnet or a coil, or as we're going to start calling them, inductors. If we take our left hand and grab the coil, and we point our fingers in the direction that the current is flowing around the inductor, our thumb will automatically point towards the North Pole. So to restate, you grab the coil. You let your fingers grab the coil in a way that your fingers are actually going in the direction of the current around the coil. Your thumb will then indicate the North Pole of the coil. When it comes to permanent magnets, there are 4 ways to demagnetize something. The first way is simply to wait. Over time, a material will naturally lose its magnetic properties. The magnetic domains in the magnet will slowly rearrange themselves back to a disarray, or a lower energy state. The opposite poles will be attracted to each other, and over time, they will diminish the overall magnetism. Another way to do it is to take an old motor stator, the stationary part, and hook it up to an alternating current. So effectively what you've created is an electromagnet where the magnetic field is constantly going back and forth and back and forth and back and forth. Since a field is going back and forth, you can take your magnetized object and put it in the alternating field. The alternating field will then interact with the magnetized moments of the object and cause them to scatter and move about in disarray. The next 2 ways is to add some sort of energy to the magnet. When you strike or hit a magnet, you send shock waves down the length of it. The shock waves, or the vibrations, will cause the molecules in the magnetic material to move. And as they vibrate, that will allow the magnetic moments or domains to move a little bit as well. If you apply enough energy and enough of a shock wave, then these domains will go back to a lower energy state, or back to disarray. If you add heat to a magnetized material, the molecules will get excited and they'll start moving around. And as the molecules move, so will the magnetic domains. And eventually the domains will put themselves back into a lower energy state. They will go back to being in disarray. Being magnetized is not a natural state for materials. most materials would prefer to be in a lower energy state, or non-magnetized. Most of our modern life wouldn't be possible without the discovery and implementation of electromagnetic machines. The list of electromagnetic machines and devices is vast and varied as you can imagine. We use electromagnetism for metering circuits. Speakers and microphones also employ electromagnetism. Transformers, which allow us to change voltage. Solenoids, which allow us to turn on and off fluids, air, pneumatics, and other things remotely. And motors and generators. It's hard to imagine what life would be without electromagnetism and the devices we've created from it. So let's do a quick review. With permanent magnets, or any magnet, like poles repel, and unlike poles attract. Some materials make better magnets than others. There are three categorizations of magnetic materials: ferromagnetic, paramagnetic, and diamagnetic. As we pass a current through a wire or a current-carrying conductor, a magnetic field is set up around that conductor. The direction of the current through the conductor will determine the direction or polarity of the field. The strength of the magnetic field is primarily determined by the ampere turns. As I increase the current, I get more magnetism. As I increase more turns or loops or wires, I also increase the magnetism. Core material concentrates my magnetic flux and makes my magnetic circuits more efficient or effective. There are different ways to demagnetize an object. We can place it in an alternating current magnetic field, we can strike it, we can heat it, or we can simply wait over time. This concludes the presentation on magnetism. Thanks for watching.